everyone, today we're going to be going through some graphs questions very similar to what you're going to see on your GCSEs. So I have got 5 different questions for you. I've got 2 about distance time graphs, I've got 2 about velocity time graphs, and then I've got 1 about an IV graph. Now, if you want the full question paper of the questions I'm going to go through today, then please check out the link in the description of this video. So let's start with a distance time graph. Now we know that for a distance time graph, the gradient equals the speed. That's the key thing to know about a distance time graph. Steeper gradient, faster speed. Shallower gradient, smaller speed. And it means that if the line is flat, so the gradient is 0, the object is not moving. Now here I've got a student walking to school, okay? And I need to calculate their speed in the first 5 minutes. But the trick here is I've actually been asked to calculate the speed in meters per second. You'll notice my x-axis here is in minutes. So when I get my change in x, when I calculate the gradient, I'm going to want to turn that into seconds. So I'm going to show you how to do this. So the gradient is calculated by working out the change in y and dividing it by the change in x. Now, this is sometimes called rise over run. So it's how much the line goes up divided by how much the line goes along. And I've been asked to find the speed in the first 5 minutes. So just for this bit to the left of this dotted line that I'm drawing here. Okay. So the change in y is going to be how much this line has gone up by. So it's gone from 0 to 400 meters. So my change in y is going to be 400. Now I need to divide by my change in x, which actually I can tell from the question because I'm told it's in the first 5 minutes. So my change in x is going to be 5 minutes, but I'm actually not going to want to put 5 minutes into my calculation because then I'm going to get my speed in meters per minute, which I don't want. I want meters per second. So what I'm going to do is I'm going to take my 5 minutes, I'm going to multiply it by 60 to find 5 minutes as seconds, because remember there are 60 seconds in every minute. So that's going to give me 300 seconds. So I'm going to do 400 divided by 300, which would give me an answer of 1.3 meters per second. So that's the speed in the first 5 minutes. Now, in B, I'm asked to describe the motion of the student between 5 and 8 minutes. So that's this bit here. Now, the gradient of my line here is 0. So that means that the speed will be 0 meters per minute or meters per second, whatever. It doesn't matter. It's 0. So the student will be stationary or standing still. Because look, the distance isn't increasing, so they're not moving. Right, for part C, I've been asked to calculate the speed between 8 and 12 minutes. So I'm now looking at this second upward sloping blue line here. So again, to calculate the speed, I need to find the gradient. So I'm going to do the change in y divided by the change in x. Now the change in y this time is going to be a little bit more tricky to work out, because this line starts at 400 and goes up to 800. So my change in y is going to be 800 take away 400, which would just be 400 meters. So the distance is changing by 400 meters. I then need to look at what the change in x is, or the change in the time is. We're going from 8 minutes to 12 minutes. So the change in time is going to be 4 minutes. Now, again, I'm going to want this in meters per second, so I'm going to need to turn my 4 minutes into seconds. So I'm going to do 4 times by 60 to get 4 minutes into seconds. I am just going to check this one on my calculator. So I'm going to do 4 multiplied by 60, which gives me my answer of 240. Perfect. So 240 seconds. So that means that I can then do, I'm just going to move this down. So the change in y was 400 meters divided by 240 seconds. I don't need a unit there. I'm going to put these numbers into my calculator and that will give me my speed. So I'm going to do 400. And then I'm just going to use this answer button here because my calculator's got a memory, so it can store the numbers in its memory. So this is going to be 400 divided by 240, and that gives me an answer of 1.666 recurring, or 1.7 meters per second. So the student is walking faster between minutes 8 and 12 than they are in the first 5 minutes. And actually, we can tell that because if we look at the graph, that second line looks slightly steeper than the first one. Right, let's get ready for a slightly trickier question then. Question 2 is a little bit trickier than question 1. It's more like something we'd see on a higher tier paper. So for part A, I need to explain what a curved line on a distance time graph shows. So a curved line means a change in gradient. Now, we know that the gradient of a distance time graph is the speed. So a change in gradient means a changing speed. Instead of writing changing speed, we could maybe say the object is accelerating. Now we can use accelerating for changing speed, depending on whether it's speeding up an acceleration or decelerating, which is slowing down. We can use the word accelerating for both. Right, for part B, we have to describe how the speed of the car in this graph is changing. So we're going to say that at time equals 0, so at the start down here, the speed of the car is increasing, because it is. We can see that the gradient is increasing as time goes on, so that means that the car is speeding up. But you'll notice that actually this curve starts to peter out. It starts to become a straight line. And I would say that after 8 seconds, so from about here, after that, that is a straight line. So the car will be moving at constant speed. So after, I'm going to write t is equal to 8. The car will be moving at constant speed. Right, now, part C is a little bit more tricky. We need to estimate the speed of the graph here, so speed of the car here, at 6 seconds. Now, that's just that little bit more tricky this time than it was in the previous question because we've got a curve. So what we need to do is we need to draw a tangent to our curve at 6 seconds, just like I've done here. So I've drawn a straight line that just touches the curve at 6 seconds. If I can find the gradient of this black straight line, then that will give me an estimate of the speed at 6 seconds. So remember that we calculate a gradient by doing the change in y over the change in x. Now, I sometimes call this rise over run. So we need to work out how much this black line has gone up. So it starts at 0 and goes all the way up here. So that would be 55, 60, 65. So that'd be 165. So the change in y is going to be 165. It's gone from 0 to 165. Now, the change in x is going to be along here at the bottom. So we're halfway between the 2 and the 4 here. So I'd say that that is going to be 3. And it goes up to 10. Now we're looking for the change in x. So I'm going to do 10 minus 3 to get 7. So it's going to be 165 divided by 7. So I'm going to grab my calculator and I'm going to do 165. I'm going to divide it by 7 and I'm going to get an answer of 23.6. So I'm going to do 23.6 meters per second. Don't forget your unit. Now, question 3 is a little bit different because question 3 is now showing us a velocity time graph. So the first question asks us to show that the acceleration of this graph is 4 meters per second squared. Now, if you ever get a show that question, it's normally a sign that you're going to have to use that number in a later question. So we're going to bear that in mind for parts B and C. So the acceleration can be calculated from a velocity time graph from finding the gradient. So the gradient of a distance time graph is speed. The gradient of a velocity time graph gives me acceleration. So I'm going to find the gradient, and I'm going to do that by doing the change in y, or the rise, divided by the change in x, the run. So I can take the whole triangle here, so I can go all the way along and all the way up. Happy days. So my change in y is going to go from 0 to 20. So the change in y is going to be 20. The change in x is going to go from 0 to 5. So my change in x would be 5. So I'm going to grab my calculator just to check my maths, and I'm going to do 20 divided by 5 like this, and it gives me an answer of 4. So my answer is going to be 4 meters per second squared, just like I was asked to show in the question. Now, part B asked me to calculate a resultant force that acts on the car. I'm given a mass and I know the acceleration. So I'm going to think, what equation do I know that's got force, mass, and acceleration in it? I know Newton's second law, force is equal to mass multiplied by acceleration. So the mass of the car, I'm told in the question, is 1,200. I'm told the acceleration of the car, I calculated that in the previous question, is 4 meters per second squared. So that's why it was a show that question. I'm going to grab my calculator and I'm going to do 1,200, multiply it by 4, and I get an answer of 4,800. So my answer is going to be 4,800. It's force. So my unit would be newtons. Now, for part C, I'm told the car stops accelerating and travels at a constant velocity after 5 seconds. I need to describe the shape of the graph after 5 seconds. So if the car has stopped accelerating, it's going to travel at a constant velocity, which means the line is going to be straight. So we're going to say a straight line at 20 meters per second. If the car stops accelerating here, it's going to have gotten to 20 meters per second and it will go no faster. So we're going to get a straight, we could even include here, flat line at 20 meters per second. And there you go. That's how we're going to answer that question. Question 4 is a little bit more tricky, and finding distance travelled from the area under a velocity time graph is on higher tier only. So if you're doing foundation and you think I haven't done that, that is correct, you haven't. We see this question mainly on the higher tier papers. So for the first part, you need to calculate the acceleration in the first 4 seconds. So 4 seconds is here, and we need to calculate the acceleration of this vehicle. So remember, the acceleration of a velocity time graph is the change in y divided by the change in x, or the rise over the run. So we go up from 0 to 8, so the rise would be 8. The run would be from 0 to 4, so the change in x would be 4. So my answer is going to be 2 meters per second squared. My acceleration for just the first 4 seconds. Now, part B asked me to calculate the distance travelled in the first 4 seconds. Now, remember that on a velocity time graph, distance travelled equals the area under the graph. So I want to find the area of this shape here. Now that shape is a triangle, and I know that the area of a triangle can be calculated by doing half multiplied by the base multiplied by the height. So that's what I'm going to do. I'm going to do a half multiplied by the base, so 0 to 4, which would be 4, multiplied by the height, 0 to 8, so 8. Now, I'm going to grab my calculator, because although I can do this one in my head, I just want to check that I'm going to get my numbers correct. So I'm going to do half. You can put a half into your calculator, or I'm just going to put 0.5 into my calculator, multiply it by 4, multiply it by 8, and I get an answer of 16. So my distance travelled will be 16 meters between 0 to 4 seconds. Now, Part C asked me to calculate the distance travelled during the entire journey. Now, looking at this shape here, that's going to be a little bit difficult to calculate the area of that in one go. So I'm going to split it up into different shapes. So I've already calculated the area of the red triangle. I'm then going to calculate the area of the green rectangle, and then I'm going to calculate the area of the purple triangle, and then I'm going to add them all together. So the area of the rectangle, now area of any rectangle is just the base multiplied by the height. So the base goes from 4 to 10. So this is going to be a length of 6. And it goes from 0 to 8. So that there is going to be a length of 8. So the area of the rectangle is going to be 6 multiplied by 8, which gives me an answer of... I'm always going to do all my calculations on my calculator just to make sure I don't get any of them wrong. 48. Perfect. So 48 meters. Then I need to work out the area of that triangle, which is going to be a half again, times by the base, so 10 to 14, which would be 4, times by the height, 0 to 8, so that would be 8. So that's going to be the same as the area of the red triangle, so 16 meters. And then I just need to add all my areas together. So I'm going to do 16 plus 48 plus 16 to find the total area. So on my calculator, I can actually just now press plus, and they will take my previous answer, which is the 48, plus 16 plus 16, and I get an answer of 80. So the total distance travelled is 80 meters. Now, for part D, I'm asked to find the deceleration between 10 and 14 seconds. Now, that's actually going to be the same as the acceleration, which is going in the opposite direction, because it's going to be the same change in velocity over the same time. It's just going to be that it's going in the opposite direction. So the acceleration would be the change in y divided by the change in x. The change in y would be minus 8 divided by 4, so it'd be minus 2 meters per second squared. It's that minus that shows us that the object is slowing down. Right, so this graph is not a distance time graph or a velocity time graph, it's an IV graph, which is sometimes what we call a current potential difference graph. So all we know is that this is just a non-ohmic conductor. And the first thing we need to do is describe the relationship between the current and the potential difference shown in the graph. So if you're ever asked to describe a relationship, this is how you do it. You say whatever's on the x-axis, so in this case, potential difference, and as that increases, what happens to the y? So in this case, we're going to say, as the potential difference increases, I'm going to write potential difference as PD, I hope you don't mind, the current increases. That's mark 1. Mark 2 comes from describing the shape of the graph. So linear, straight line, non-linear, curve. This graph is non-linear, so the graph is non-linear. And bosh, there we go. 2 marks. Perfect. Next up, I need to explain why this component is non-ohmic using the graph. So don't forget that an ohmic conductor means that current is directly proportional to the potential difference. If this was an ohmic conductor, so current was directly proportional to the potential difference, we would see a straight line going through the origin. So Ohm's law states at constant temperature, current is directly proportional to the potential difference. This would be shown by a straight line through the origin. Okay, we don't have a straight line through the origin, so therefore this is going to be a non-ohmic conductor. Right. Part C asks us to describe how the resistance of the component changes as the potential difference increases. So, as we look at this graph, the gradient is getting shallower as we go up. So, as the potential difference increases, the gradient on a current potential difference graph is the inverse of the resistance. So if the gradient gets shallower, that means the resistance is getting larger. Just like you think about like a filament lamp, for example, where we know that it makes that kind of classic almost S shape like that. We know that as the line begins to bend down, that's because the resistance is increasing. So it's going to be exactly the same here. So as the potential difference increases, the resistance increases. Then finally, I'm being asked to calculate the resistance of the component at 8 volts. So I'm going to go up from 8 here. So at 8 volts, I know that my current is about halfway between 2.2 and 2.3 amps. So that current reading is going to be 2.25 amps. So I know the equation V is equal to I multiplied by R. The potential difference is going to be 8 volts, as you can see here. The current is going to be 2.25, and I need to find the resistance. So I'm going to rearrange this equation. I'm going to divide both sides by 2.25, and then I'm going to pop the numbers into my calculator, because I definitely can't do those ones in my head. So I'm going to do 8 divided by 2.25, which gives me an answer of 3.55555, or 3.6 ohms. And there we go.